Over here I have what we call a gas jar, and I've put water in it. And you see the water doesn't come out until some air goes in. Well, I'm going to use the oxygen cylinder to fill the gas jar with pure oxygen. And notice how it displaces the water downwards. So we call that collecting a gas by the downward displacement of water. I've already got a few others waiting. I let a bubble escape, so I end up with a small amount of water at the bottom. Here I have a gas cylinder and a little Bunsen burner. So let's turn it on. You see, this is a very cool flame. It's a very orange flame. If I hold it like that, you can see there's a lot of unburnt carbon. It's not an efficient flame. But if I open this little hole at the bottom, and you might be able to hear it, it's really roaring as it sucks the air in, and so the burning is far more efficient. Right, so here we have a candle, and let's see what it looks like burning in pure oxygen. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 seconds before it all goes out. I'm using the water to fill it and thus flush all the carbon dioxide out. Let's see how long the candle lasts in pure air. 1, 2, 3. Only 3 seconds, whereas it lasted a lot longer in pure oxygen. The next element I'm going to combust is that of sodium. Sodium is a very reactive metal. It's one of the group 1 metals on the periodic table. Notice how I'm handling it. I don't want to touch it with my fingers if I can avoid it. And if you're able to zoom in here, can you see inside the bottle? The sodium is so reactive that we want it not to be in contact with air or oxygen, and so we store it in oil or paraffin. It is rather a soft metal. This might be a new idea to you, but notice how I can cut through it with a knife. And if you can zoom in really close there, you might be able to see how shiny it is. I only need a small bit to combust, but before I do that, I want to show you what it does in water. Sodium is very reactive. I'm going to drop a small piece in the water. Notice how it's buzzing around the surface. And while it does, it appears to disappear. Well, the sodium dissolves, and it's buzzing around the surface because it makes hydrogen gas. But hydrogen gas explodes. So let's see if I can do that again, but collect some of the hydrogen this time.
To have the water in.
I'm going to try and get this to fit in the water, but collect the gas inside the test tube. There we go. That's what I wanted. Now you can see it buzzing around inside the test tube. If I pull that out, let's see if I had enough hydrogen gas. We're going to zoom in here. And it makes a characteristic popping sound. Right, I'm going to take a small piece of sodium. I'm going to melt it. Notice the yellow color as the sodium starts to burn. There it's melting, and I put it in there, and we see it burns with a nice yellow flame. Unfortunately, even the cork is caught on fire. So, unfortunately, the sodium didn't all burn, and the cork's burning, but there is some sodium left on the spoon. So when I push it into the water, it's actually going to react with the water as well. Now the spoon is rusting, and that is why the water's gone brown. So I've got a piece of pink litmus and a pink piece of blue litmus. I'm interested to see if there's going to be a color change. So we put them like that, and we're just going to moisten them with the liquid at the bottom. And hopefully you can see very nicely how the pink litmus went blue. The next one we're going to do is that of magnesium. Magnesium burns very well in air, and it doesn't really need pure oxygen. It is a very bright flame, and if I put it in pure oxygen, it's even brighter. When I pull it out, I'd like you to zoom in on there and see if you can see the magnesium oxide. It is a white powder, still in the shape of the ribbon. I'm going to dip that into the water and see what effect that has on litmus paper. Again, I take pink and blue litmus and I moisten it on the sides and wet it with water. If you can zoom in there, is it clear? You can see that the pink litmus went slightly blue. Magnesium oxide is only partially soluble in water, and so it is weakly alkaline. It is in group 2 in the periodic table, magnesium, and is called an alkali earth metal. The third one I'm going to do is that of iron in the form of steel wool. Now, steel wool is finely divided. The Bunsen burner isn't really enough heat to melt the iron, but if I can get it just glowing enough, let's do it like this. If I can get it glowing just enough, I might be able to see the reaction of iron with pure oxygen. Make that a bit hotter. Don't heat it very much, and I put it in there. And if you can zoom in close, you might have seen those little bursting flames. It's like a sparkler. One of those things that you see at Guy Fawkes or at the Spur when they have birthday parties for children. The sparkler has got iron filings in a paste that makes oxygen. Let's immerse this in the water. Iron oxide does not dissolve in water. But you'll see a little bit of the brown. The spoon itself is also made of iron, and it's been used many times, and that is why it is so rusted. Again, I take my 2 pieces of litmus and I'm going to try and see what the effect is. Zoom in there. Notice the blue stays blue and the pink stays pink. Iron oxide does not dissolve in water, and so it is neither alkaline nor acidic. The fourth one we're going to do is that of sulfur. Sulfur is in the form of a yellow powder. I've put it on the spoon, the deflagrating spoon. I heat it, and you will see it start to melt. I need to get it to catch a light. And I think it has, and I put it in the pure oxygen, and we see it burns with a nice blue flame. Sulfur is a non-metal, and the oxide is called sulfur dioxide, and it is a gas. So you're seeing some smoke here, which is little particles of sulfur, but there's also sulfur dioxide. If you breathe it in by mistake, it makes you cough, and we say it has a choking smell. So this jar is now full of sulfur dioxide, and it dissolves very well in water. So I'm shaking it up to dissolve in a little bit of water, and now I'm going to test it with litmus again. Again, I take my pink and blue litmus, and you can see almost instantly how it goes pink. It's fallen down on the bottom. Let's see if I can get it to stick to the sides. So the pink litmus stays pink, and the blue goes pink, which is an indicator that the oxide is an acid. Sulfur dioxide dissolves so well in water that when it's an impurity in the air, it comes back to the earth as acid rain, particularly a problem in Mpumalanga, where we have sulfur impurities in the carbon. And so we get tons of sulfur dioxide going into the atmosphere, which then dissolves in the rain and comes back down to the earth as acid rain. The last one I'm going to do is that of charcoal. Now, we used to charcoal at a braai. At the moment I'm heating the spoon mostly, so I'm going to try and heat it from above. And we know what charcoal looks like when it burns. It burns with an orange flame. So I get it going, I put it in pure oxygen, and we see there's a few little sparkles there. That's some of the powder carbon. That's the convection currents are busy making it fly off the spoon. But we, again, will see how long it burns for. And so, like the candle, pure carbon with oxygen makes carbon dioxide. Carbon dioxide is a gas, and it's a colorless gas, so you can't see anything here, and there's very little smoke. So we just need to be patient. It will take some time before it uses up all the oxygen. I'm going to stop it there, even though it was still glowing, and try and get some of the carbon dioxide to dissolve in the water. Carbon dioxide in water forms very weak carbonic acid. That's what fizzy drinks are. Again, I'm going to take my 2 strips of litmus, my pink and my blue. Oops, I dropped them in. Let's shake that up. And the pink stays pink, but I don't know if you can see there that the blue has gone very slightly pink. Let's write some chemical formulae for the reactions we've just seen. The metals, see page 90 of your textbook, form alkaline oxides. They turn the indicator litmus from pink to blue. Sodium burnt with a yellow flame to form sodium oxide, and this is the formula. Notice in the molecule we have 2 oxygen atoms, but in the final formula only 1. Well, we need to have the same number of atoms in the beginning, the reagents, as there are at the end, the products. If we started with 2 oxygen atoms, then we need 2 of these units. 2 of these means 2 times 2 equals 4 sodium atoms at the end, which meant we needed to have 4 to start with. Magnesium. Similarly, we need to have 2 of these at the end, and therefore also 2 magnesium atoms to start with. Steel wool, iron. In the final formula, there are 3 oxygen atoms. We cannot make 3 equals 2, but we can make them both 6 by having 2 of these units. 2 times 3 is 6 oxygens, which meant we needed 3 of these molecules. 3 times 2 is 6 oxygens at the beginning. 2 of these means 2 times 2 equals 4 iron atoms, meaning we needed 4 to start with. That's the process of writing balanced chemical equations. The nonmetals form acidic oxides. They turn the indicator litmus from blue to pink. Carbon, that's already balanced, that equation, burnt with an orange flame, forming carbon dioxide, and sulfur formed sulfur dioxide, burning with a blue flame.